done soon. So I'll be covering the electricity network and the use of machine learning to help with clean energy network data. So let's first start off with the role of data in the energy transition. So you see some growth areas at the top. So the value to be captured globally through digital transformation of the electricity sector alone between 2016 and 2025 is valued at $1.3 trillion. And the global smart utilities market size is valued by 2030 is valued at $7 trillion. And most of that is coming from the electricity sector. You may be wondering why it's the electricity sector, and that's because, you may be wondering why it's the electricity sector, and that's because within the utilities, the electricity sector is going to be the single largest contributor to our decarbonization efforts. The other utilities, such as water and gas, are going to play a big part too, but their main theme to decarbonize is going to be feeding energy from low-carbon technologies, from low-carbon energy sources, and that again feeds into the electricity grid. So yeah, like I mentioned, the electricity grid is going to be the largest contributor to our decarbonization efforts, and to do so, especially with the electrification of heat and electric vehicles and transportation, we're going to need to adopt a lot more low-carbon technologies. And the low-carbon technologies that we're talking about is solar, wind, and all the technologies that support this. And to adopt these low-carbon technologies, you need to modify the network, and that's where decentralization comes into play. So decentralization is the concept of going from a distribution network operator to a distribution system operator. And that means that we're going away from the traditional big power plant that supplies 2 million or 3 million of houses to a more dynamic network where different renewable energy sources are feeding into the grid at different times and at different places. And that's going to make the grid a lot more dynamic. And that's where some of the challenges come into play. So the grid is very well designed to go from low voltage to high voltage to low voltage, but it isn't designed so well to go the other way around. And so to deal with this, we need to, again, look at infrastructure modification. And this is where the role of data comes into play. You need that data to understand not only the network, but to drive those intelligence-led decision-making capabilities that you need, especially when it comes to infrastructure investment. You need to be able to prioritize which parts of the grid that you need to invest into and the ones that you can delay. And that brings me to the last point, which is data quality issues. Now, many DNOs, as well as many asset companies, actually struggle with good oversight of their networks, but also their assets. And that brings me to the recent project that we've done for WPD. So WPD stands for Western Power Distribution. It is a electric utility company in the UK that serves the Midlands, the southeast of England, and south of Wales. And approximately has 220,000 kilometers of overhead and underground cables. And it's recently been acquired by National Grid. So if you're looking for WPD, you may be confused if you see National Grid. It's called National Grid now. So what was WPD struggling with? Now, like many electric utility companies, WPD has a lot of assets. I think tens of millions of assets alone for WPD. And so when they were looking at their network, you had lots of data that was being compiled over many years. Sorry. It's okay, I'll stay here.
No, because they cannot listen to you, man, because you're moving away from the camera. So you use that?
Yeah, it's all right.
You don't want to use that?
It's all right, yeah, I'll stay with this. My bad, sorry. Where was I? So the data has been compiled many years through different systems, through different acquisitions, and that has left a lot of misunderstanding and incorrect and inaccurate data with regards to their network. And when you look at the WPD, again, owning tens of millions of assets, most of the assets, or 90% of those assets, are in the low voltage networks. And so errors here can go undetected. And fixing this is going to be incredibly costly, incredibly complex, and that's why we looked at the use of machine learning to help clean this energy network data. So the solution that we delivered comprises of two models. So you have the connectivity model and the spatial graph model. The connectivity model focuses on the customer connectivity in the low voltage networks. It is a domain-focused, rule-based model that is based on a functional graph, and it uses algorithms like MaxFlow and MinCut to identify inconsistencies. The spatial graph model, which is the more interesting one, is a data-driven model that uses machine learning to learn patterns in existing data and provide the relevant and the right, accurate information regarding the asset. Now, you'll also notice that I talked about the spatial correlation, and this is the concept of the strong spatial correlation that assets have, and not just connected assets, but non-connected nearby ones. And the premise behind this is that if assets are in close proximity to each other, they're more likely to have been installed at the same time. They may have the same kind of properties, and so they may exhibit the same kind of characteristics. So just to give you a brief overview of the concept here, so you have the GIS data that we get. We then develop a spatial graph structure, and then we apply machine learning to it to get the corrected attributes. Now, if there is a difference between the corrected attributes and the observed attributes, then we'll know that we have an error here. So delving a little bit deeper into the two different models here, we have the spatial graph, and the concept here is that we turn assets into nodes, and then we assign those assets with the right attributes. And as you do this for all the assets through the network, then you build up a spatial graph where each connected asset is connected to its nearby one through a spatial mesh. Now, the benefits of the spatial graph is that it's easy to use, it is flexible, and it is also very, very powerful. And it can also be extended with any kind of spatial data. So if you are looking at properties, if you're looking at consumer data, that you can add to the model. And the more information that you add to the model, the better that the model should perform. Now that you have a spatial graph, you can now apply machine learning to it. And the machine learning technique that we use is graph neural networks. And graph neural networks are incredibly powerful. They're a novelty, and they're a big space in the space of data science right now. We didn't use it because it's a big topic, but we used it because of these key desirable traits here. It is inductive, so it's able to predict for unseen data. It's able to combine relationships of the graph with feature vectors, and it also it has the ability to scale. And we're looking at, in the future, of scaling the whole network rather than a smaller area. So what was the outcome for WPD? Now, it was incredibly successful. I think the accuracy of the results were very high, around 98%, which is good. Because most of the assets, most of the vast majority of the attributes were identified as no error, and the highest amounts of accuracy were in the no errors space. It also has the ability to, the WPD were able to find out that machine learning techniques can be used to identify errors and suggest corrections using just a limited amount of information. So if there's a lot of missing information, this model can still work. And this brings me to the last topic as well, is that it's an inductive model, it's also flexible, and it can address a broad range of issues. There's nothing about this model that we used for this electric company that is just exclusive to the electricity nature of the network. You can apply these to different applications. So this here is called presumed open data. So presumed open data is the premise that your data should be in a relatively good condition that even third parties can use it. You also have the other critical infrastructures like gas and water. They have the same kind of issues, a significant network of assets. Lots of the information is missing. I believe in the sewer networks, there's a lot of areas where it's not properly or accurately mapped. So this solution could work really well there. Outside of the utilities, again, there's many types of companies that have this kind of issue. One of them is telcos. They suffer as well from a large inventory of legacy systems. It is costly, it is very messy, the data, and it's one of the reasons why inventory migration is one of the costliest and riskiest things to do in the telco industry. And then also other, and that is other use cases that haven't been identified yet because it was always presumed that the data was not available. And that brings me to the end of the presentation. Now, on the left-hand side, you'll have a QR code that'll take you to the National Grid's website, so you can find out more about this project itself. On the right-hand side, that's a QR code that'll take you to my LinkedIn page, and if you want to get in touch with me, I'm happy to answer any questions. Thank you very much.